Hello, I'm Hossein, and welcome to another tutorial on this channel. If you have ever seen models such as car bodies, computer mouse, game controllers, bottles, or even 3D characters, there is a very good chance that they were created using a method called subdivision modeling, or simply SubD. SubD is one of the most important features that has been added to Rhino in recent years. It has transformed Rhino from a tool focused mainly on precise engineering modeling into a powerful solution for creating smooth, complex, and organic shapes. However, many people who are new to SubD usually face two common challenges. Some only learn a few commands without understanding what is actually happening behind the scenes. Others know the tools, but still struggle to create the forms they imagine. The reason is that SubD is not just a collection of modeling tools. It is a completely different way of thinking about shape creation. In this video, we will explore SubD from the ground up, step by step. First, we will talk about its main concepts and the logic behind how it works. Then, we will move on to the essential tools and commands inside Rhino, learn how to use each one, and finally discuss the key principles that will help you create cleaner, more professional, and more controllable models. So, if you want to learn SubD properly, let's get started. Before we start working with the tools inside Rhino, it's important to first understand what SubD actually is and why it has become such an important part of 3D modeling. Many people think that SubD is simply a command for smoothing or making models softer, but that is not the case. SubD, or subdivision surface, is a modeling method. This means we create the model based on this concept from the very beginning, rather than simply making the final shape look smoother at the end. In this workflow, we do not directly edit the final surface of the model. Instead, we create a simple network of vertices, edges, and faces, which is called the control cage. This control cage works like the skeleton of the model. Every change we make to this structure is automatically used by the software to calculate the smooth, final surface. In Rhino, this concept is very easy to see. If we have a SubD model and press the tab key on the keyboard, we can switch between two different views. In the first view, we only see the control cage, or the original network. This is the actual structure we are editing. In the second view, we see the smooth final surface, which is generated based on that simple cage. This is one of the most important ideas in SubD, and I recommend paying close attention to it from the beginning. Because from this point forward, whenever we move a vertex, add an edge, or change the shape of a face, we are actually editing the control cage, not the final surface itself. Once you fully understand this difference, the behavior of SubD becomes much more predictable and controlling complex smooth forms becomes much easier. Now that we understand the basic concept of SubD, let's take a look at why Rhino introduced this feature and what problem it was designed to solve. Why did Rhino need SubD? If we go back a few years, Rhino was mainly known as a powerful software for NURBS-based modeling. NURBS modeling provides extremely high precision and is one of the best choices for industrial design, manufacturing parts, mold making, and projects where dimensions and accuracy are critical. However, when it came to creating soft, freeform, and organic shapes, the process became more challenging. Imagine you want to design the body of a car, a computer mouse, a game controller, or any product with smooth and continuous curves. It is possible to create these forms using NURBS, but usually it takes more time and requires careful control over many different curves and surfaces. Because of this, many designers would create the initial form in software such as Blender, Maya, or 3ds Max using subdivision modeling, and then transfer the model to Rhino later if needed. Adding SubD to Rhino helped close this gap. Now we can create smooth and complex forms directly inside Rhino, without having to move between multiple software packages. One of the biggest advantages of SubD in Rhino is that, when needed, we can convert a SubD model into NURBS surfaces. This allows us to take advantage of the precision of NURBS for further design work, manufacturing, or preparing files for production. That is why Rhino today gives us both the accuracy of NURBS modeling and the flexibility and speed of SubD modeling. Of course, this does not mean that SubD has replaced NURBS. Each method was designed for a specific type of modeling, and once you understand both workflows, you can choose the best approach depending on the needs of your project. How does SubD work? In SubD, we do not directly edit the final surface. Instead, we modify a control cage, and Rhino calculates the smooth final surface based on that structure. This process is done through a method called subdivision. In this method, the model's mesh is divided into smaller sections while becoming smoother at the same time. Rhino uses the Catmull-Clark algorithm for this process, which is widely used in product design, animation, and game development. During subdivision, the faces are divided into smaller parts, and the positions of the vertices are recalculated to create a continuous and smooth surface. This means that every change made to the control cage affects the final result. For example, moving a single vertex will smoothly influence the surrounding area, while adding an edge can make a shape more controlled or sharper. That is why the most important concept in SubD is the topology of the model, the way vertices, edges, and faces are connected together. A clean topology gives you better control over the form and leads to a higher quality final model. In the end, every edit in SubD means changing the control cage, while Rhino continuously generates the smooth final surface in real time. Now we are entering Rhino and looking at the first group of SubD tools. Just like in traditional modeling, SubD also provides a set of basic starting shapes or primitives, which are a great foundation for building different models. In most projects, you don't need to build everything from scratch. Instead, you usually start with the primitive that is closest to your intended form. This helps you work faster and also results in cleaner topology. Let's go through these primitives one by one. The first command is box SubD. As the name suggests, it creates a SubD box or cube. After running the command, you first define the base dimensions and then set the height, just like a standard box. In the command line, you also get several important options. For example, you can control the number of subdivisions along the X, Y, and Z directions. The higher these values are, the more faces your model will have, giving you more control over detail. However, more is not always better. A common mistake beginners make is starting with too many subdivisions from the beginning. This only makes the model heavier and harder to control. Whenever possible, start with the lowest level of detail and only increase edge density when you actually need more control. The next primitive is sphere SubD. This creates a SubD sphere. At first glance, it may look like a standard sphere, but if you display the control cage, you'll notice that its topology is specifically designed for SubD workflows, allowing smooth and predictable deformation. This primitive is commonly used for organic forms, character heads, or any spherical shapes. The next command is cylinder SubD. This creates a SubD cylinder. Here, you can define the radius, height, and the number of subdivisions around the cylinder and along its height. If you are designing products like bottles, cups, tool handles, or any cylindrical parts, this is often a very good starting point. Next is cone SubD. Its behavior is similar to the cylinder, but with different top and bottom radii, resulting in a tapered or cone-shaped form. This is especially useful for designing objects that gradually narrow or widen. And finally, the torus SubD. This creates a ring or donut-shaped SubD object. You can control the main radius, tube thickness, and subdivision levels. It is not only useful for rings in many industrial designs, it can also serve as a strong base for more complex forms. One important point that applies to all SubD primitives is that you can adjust the subdivision levels during creation. More subdivisions mean more faces and more control, but also a more complex and harder to manage model. So always try to start with the simplest possible primitive and only add detail when it is truly necessary. Now that we are familiar with the main SubD primitives, it's time to move on to one of the most important editing tools in Rhino, the Gumball, and see how we can start shaping these simple forms into the designs we want. So far, we have only created basic shapes, but the real power of SubD begins when we start transforming and reshaping these forms. The most important tool we use for this purpose is the Gumball. If you have worked with Rhino before, you are probably already familiar with Gumball. It allows us to quickly move, rotate, or scale the model without having to run different commands. On the Gumball, you will see 3 different types of controls. The arrows are used for moving the object along each axis. The curved handles are used for rotating the model, and the small squares between the axes are used for scaling or changing the size. One of the great features of Gumball is that it is not only used for moving the entire model, we can also use it to modify different parts of a SubD object individually. Before doing that, let's take a look at one important Gumball setting. If we right-click on the Gumball, several options will appear. One of the most important ones is Align to World and Align to Object. In Align to World mode, the Gumball axes always follow Rhino's main world axes. This means that even if we rotate the model, the Gumball directions remain unchanged. But in Align to Object mode, the Gumball axes follow the direction of the selected object, or part of the model. When working with SubD, both modes can be useful, and you can switch between them depending on the situation. Now let's move on to the most important part of SubD, editing the components of the model. In SubD, we don't only select the entire object, we can also edit its individual components separately. To do this, hold Ctrl plus Shift and click on the model. Depending on where you click, you can select a vertex, an edge, or a face. Now, if you move the Gumball, only that specific part will change, while the rest of the model smoothly adapts to the modification. This exact behavior is the foundation of SubD modeling. There is another very useful feature as well. If you double-click on an edge, the entire edge loop will be selected. This allows you to quickly work on a complete loop of edges without manually selecting every single edge. So if selecting loops feels difficult at first, spend some time practicing it, because it is one of the most important skills in SubD modeling. So far, we have learned how to start with primitives and use the Gumball to transform their shapes. But we are not always going to build a model from a basic volume. In many projects, we may already have the required curves or profiles, and we want to create a SubD model directly from them. Rhino provides several dedicated commands for this purpose, which we will explore now. The first command is Extrude SubD. If you have worked with the regular extrude command before, the workflow will feel very familiar. First, we select a curve or a face, and then by defining the direction and distance of the extrusion, Rhino creates a SubD volume. This is one of the fastest ways to create simple forms and is often a great starting point for many models. The next command is Loft SubD. With this command, we select several curves in order, and Rhino creates a SubD surface between them. The more suitable the shape and arrangement of the curves are, the cleaner the final result will be. This command is especially useful for designing forms that gradually change their cross-section, such as bottle bodies, tool handles, and many industrial products. The next command is Revolve SubD. If we have a 2D profile, we can rotate it around an axis to create a SubD model. Almost any object with rotational symmetry, such as vases, cups, bottles, or many industrial components, can be created easily using this command. Now we move to sweep one rail SubD. In this command, we first select a rail and then one or more sections. Rhino moves these sections along the path and generates a SubD model. The more organized the path and sections are, the more controlled the final shape will be. The sweep 2 rail SubD command works in a similar way to sweep 1, but this time we use 2 rails. Having 2 rails gives us more control over the final form and makes it a better choice for models with more complex shape changes. The final command in this section is Multi-Pipe SubD. This is one of the most interesting SubD tools in Rhino. All we need is a set of curves, or a network of lines. Rhino automatically creates pipe-like forms along these paths and smoothly blends all the intersections together. This tool is extremely useful for creating frames, tubular structures, branching forms, and even concept designs. In many projects, it can reduce hours of modeling work. As you can see, these commands provide different ways to create a SubD model. Choosing the right command depends entirely on the type of shape and the project you are working on. In real workflows, we usually don't rely on a single command. Instead, we combine different methods to reach the desired form faster and more efficiently. Thank you for staying with me until this point in the video. If you found this tutorial helpful, I would really appreciate your support by liking the video, subscribing to the channel, and sharing your feedback. These small actions help the channel grow and give me the motivation to create more tutorials. Also, feel free to share your thoughts about this video, the channel, or any topics you would like to see in the future in the comments section. I read your comments, and I always try to use your suggestions and feedback to improve future videos. If you haven't subscribed to the channel yet, make sure to do it now and turn on the notification bell so you don't miss the upcoming tutorials. By the way, I recently created a Telegram channel as well. You can find the link in the description of this video. There, besides updates about new videos, I will also share practice files, extra tips, additional resources, and content that I don't always have enough time to cover inside the tutorials. So if you would like to stay more connected, feel free to join that channel as well. Now, let's continue with the tutorial. Now that we are familiar with different ways to create SubD models, it's time to move on to the more important part, editing the model. In SubD, creating the initial shape is usually only the first step. The real design process begins when we can control the form, adjust edges, add details, and manage the model's topology. In this section, we will explore the main SubD editing commands. The first command is smooth. This command is used to make the model's form smoother. Sometimes, while moving vertices or edges, parts of the surface may become uneven or slightly distorted. With smooth, we can reduce these irregularities and create a softer transition between different areas of the model. However, it's important to remember that smooth is not always the final solution. If the topology of the model is not correct, simply smoothing the surface will not create a professional result. In SubD modeling, we need to build a proper structure first, and then use smooth as a refinement tool. The next command is slide edge. This command allows us to move an edge along the surface without significantly changing the overall shape of the model. Imagine we have an edge loop that is slightly too close or too far from the desired location. Instead of deleting the edge and creating it again, we can simply use slide to reposition it along the surface. This tool is especially useful when we want to control exactly where a shape transition happens on the model. One of the most important SubD tools is insert edge loop. As the name suggests, this command adds a new edge loop to the model. But why do we need to add edges? Because in SubD, edges are the main tools for controlling the form. Wherever we have more edges, we have more control over the shape, and the surface becomes less free to smooth. For example, if we want a specific area of the model to become sharper or more defined, we usually create that control by placing edge loops closer to that area. Of course, adding too many edges is also a mistake. Adding unnecessary edge loops will make the model heavier and harder to manage. The next command is bevel SubD. In the real world, most objects do not have perfectly sharp edges. Even a simple object like a device body or an industrial product usually has slightly rounded or beveled edges. Bevel SubD is used to create these types of edges. With this command, we can select one or more edges and create a smoother transition in that area. This tool is especially useful in product design and hard surface modeling with SubD. The next command is inset SubD. This command divides a selected face inward and creates a new structure on that surface. Inset is useful when we want to add details to a specific area. For example, a button location, an indentation, a panel, or a separate section on the surface of the model with inset. We can create more control over a specific area without disrupting the overall topology of the model. So far, we have looked at tools that are mainly used for changing the shape of the model and adding more control. Now we are going to explore tools that work more directly with the internal structure of the model, meaning the SubD topology. With these tools, we can remove parts of the model, combine elements, create new space, or refine the form with more precision. The first command in this section is expand SubD edge. This command is useful when we want to extend an edge or a group of edges on the model. Instead of simply moving an edge, expand allows us to create a new area and gain more control over the surrounding form. This tool is especially helpful when we want to extend a part of the model or create more space for further design changes. The next command is subdivide SubD. This command increases the number of subdivisions in the model. In other words, existing faces are divided into smaller sections. As a result, the number of edges and vertices increases, giving us more control and more detail for editing. However, there is an important point to remember. Subdividing is not always the right choice. If we do it before the main form of the model is complete, we only increase the number of elements and make the shape harder to control. It is better to first develop the model using a simple topology and only add more subdivisions at the final stages when needed. The next command is merge SubD face. This command does the opposite of subdivide. With merge, we can combine multiple faces together and reduce unnecessary subdivisions. This is useful when an area of the model has become too dense or contains extra edges. One of the important skills in SubD modeling is avoiding unnecessary complexity. Sometimes the best improvement is simply removing extra structure. The next command is delete SubD face. With this command, we can remove one or more faces from the model. This creates an open area in the geometry. Deleting faces can be useful for opening part of the model, creating a hole, or preparing the object for further modifications. However, we should remember that removing faces affects the structure of the model and needs to be done carefully. After deleting a face, we may need to fill the empty area again. This is where the fill SubD hole command is used. This command attempts to create a new surface and close the existing opening. For simple holes, it usually produces very good results. But if the surrounding topology is complex, we need to check whether the new structure is clean and suitable. The next command is reflect SubD object. This tool is used for creating symmetrical models. In many designs, such as vehicles, industrial products, or consumer objects, we usually design only one side of the model and create the other side as a mirror. With Reflect SubD, we can do this quickly, and when symmetry options are enabled, changes made on one side can automatically appear on the other side as well. This method can save a significant amount of modeling time. The next command is radiate SubD. This tool is used for creating forms where the geometry spreads outward from a central point or area. In some models, we need edges to flow from a specific region toward the surrounding areas. Radiate helps create this type of structure more efficiently, set per face color by FacePack. This command is related to controlling sharpness and smoothness in different areas of the model. In SubD, the main goal is usually to create smooth and continuous forms, but sometimes we need certain areas to behave with a sharper definition. With this tool, we can control which parts of the model should have a sharper or more defined appearance. The final command in this section is offset SubD. This tool creates a new surface at a specific distance from the existing model. In other words, it allows us to create thickness or a shell around the object. This feature is very useful for designing parts that require thickness, such as product housings or external shells. So far, we have covered almost all of the main steps involved in creating and editing a SubD model. But one of the important features of Rhino is that it allows us to move between two different modeling worlds, SubD and NURBS. As we mentioned at the beginning of this video, each of these methods was designed for a specific purpose. SubD is excellent for creating smooth, complex, and organic forms. On the other hand, NURBS gives us extremely high precision for engineering modeling and manufacturing accurate parts. Now let's see how the conversion between these two methods works. The first command is convert object to NURBS. Using this command, we can convert a SubD model into NURBS surfaces. This becomes useful when we have created the main shape using SubD, but we need to continue working in a NURBS environment. For example, precise engineering modifications, preparing files for certain manufacturing processes, using tools designed specifically for surface modeling. However, there is an important point to keep in mind. When a SubD model is converted into NURBS, its structure changes. Instead of a simple and flexible SubD model, we usually end up with a large number of individual surfaces. Because of this, converting too early can make the model much harder to manage. It is usually better to complete all major form adjustments inside the SubD workflow and keep the conversion to NURBS for the final stages. Convert object to SubD. Now let's look at the opposite process, converting an existing model into SubD. With the convert object to SubD command, we can convert certain NURBS models or surfaces into a SubD structure. This is useful when we already have an initial form and want more freedom for organic editing and shape refinement. However, the result of this conversion is not always the same. Models with cleaner topology and simpler forms usually convert much better. But if the model is very complex, with many surfaces, irregular edges, or heavy details, the final result may require additional cleanup and adjustments. One important point in professional workflows is that we should not think of these conversions as a magic button. SubD and NURBS are two different ways of thinking about modeling. The best approach is to use each one where it performs best, meaning SubD, initial form creation and freeform design, NURBS, precision, dimensions, and engineering stages, and whenever needed, move between these two environments to get the best result. So far, we have learned the main SubD tools. But creating a professional model requires more than just knowing the commands. In SubD, the way we work and the structure of the model are extremely important. Now, let's look at some important rules that will help you build better models. Rule 1, use quads. Whenever possible, try to build your model using quads. SubD works best with four-sided faces, and this helps create smoother surfaces with better control. Rule 2, every edge loop should have a purpose. Every edge should have a reason to exist. We add edges to control the shape, create sharper transitions, or add specific details. Adding unnecessary edges only makes the model heavier and more difficult to manage. Rule 3, form first, details later. One of the most common mistakes is adding details too early. In SubD, always focus on creating the main volume and overall shape first, and only then move on to smaller details. Rule 4, do not overcomplicate the model. A simpler model usually gives us more control. Try to achieve the desired shape with the minimum number of faces possible, and only add extra topology where it is truly needed. Rule 5, use symmetry. If your model is symmetrical, there is no need to build both sides separately. Using tools like Reflect, you can design one side and generate the other side automatically. This not only increases your speed, but also reduces mistakes. In the end, a good SubD model is not the one with the highest number of edges. It is the one that has exactly the right amount of control for the shape you want to create. When should we not use SubD? So far, we have seen how powerful SubD can be for creating complex and smooth forms. However, despite all of its advantages, it is not always the best choice. Every modeling method is designed for a specific purpose, and SubD is no exception. The first case is projects that require very high engineering precision. For example, parts that need exact dimensions, specific tolerances, or strict manufacturing standards. In these situations, methods like NURBS and solid modeling are usually a better choice. The next case is architecture and BIM-based projects. In these types of projects, accurate information, dimensions, walls, structures, and engineering elements are usually more important. SubD is generally not the primary tool for this kind of workflow. Also, for some completely hard surface and mechanical designs, using SubD may not be the most efficient approach. If a part contains precise holes, exact angles, mechanical connections, or detailed engineering features, more accurate methods such as NURBS can provide much better control. So, SubD is usually the best choice when we are working with forms that require fast shape modification, smooth curves, freeform design, and flexible control over the form. Knowing when to use a tool is just as important as learning how to use it. Now that we understand the logic of SubD, its tools, and the correct workflow, let's have a quick final overview. Alright, in this tutorial, we learned the basics of SubD in Rhino. We saw that SubD is not just a tool for smoothing models. It is a professional approach for creating and controlling 3D forms. We explored the main tools, learned how to edit SubD models, and understood the principles of building clean topology so we can design more complex shapes with greater control. In the end, we learned that in SubD, the most important thing is not just knowing the commands, it is understanding how to control the form and follow a proper modeling workflow. If you found this tutorial helpful, make sure to hit that like button, subscribe to the channel, and support the channel so I can keep creating more tutorials. Stay tuned for the next videos. Thanks for watching and being with me.